Okay, so think about this. When a machine is trying to find a pattern in data, it can draw a literally infinite number of lines through it. So out of all those possibilities, how does it find the one, the single best line? And for that matter, how does it even define what best means? Well, that's exactly the question we're going to unpack right now.
So here's our roadmap. First, we're going to figure out what best fit even means to a machine. Then we'll see how we can measure all of a model's mistakes and boil it all down to a single number. After that, we'll visualize that number as a giant valley, use a little bit of calculus to find the absolute bottom of it, and then finally, we'll give this whole process its official name and talk about why this is such a cornerstone concept in all of machine learning.
All right, let's start at the beginning. We've got a bunch of data points, right? And our goal is to draw one straight line that slices through them as accurately as it can. But, accurately is kind of a vague human word. For a machine to get it, we need a really precise mathematical way to score the goodness of any line it draws. We start by measuring just one mistake at a time. So for any single data point, we just look at the vertical gap between where that point actually is and where our line predicted it would be. That little gap right there, that's called the error. Sometimes you'll hear it called the residual. It's the basic building block for figuring out how well our model is doing. Okay, so if we can measure each individual mistake, the next step seems pretty obvious, doesn't it? Let's just add them all up, get a total score. And the lower the score, the better the line. But it turns out there is a massive flaw in that simple logic. So let's take an example. For this point here, maybe our line was a little too low. The actual data point was higher than our line's prediction, so that gives us a positive error. Let's say plus 0.5. But then, for this other point, our line was a bit too high. This time, the actual value was lower than the prediction, giving us an equal and opposite error of minus 0.5. So what happens when we add them up? Well, positive 0.5 plus negative 0.5 equals 0. The total error is 0. But our line is obviously not perfect. The problem is the positive and negative errors canceled each other out, giving us a totally misleading score. We've got to fix this. And the solution is actually this really elegant little math trick. We just square every single error. Think about it. What happens when you square a negative number? It becomes positive. A positive number stays positive. So by squaring them, we guarantee that every single mistake, no matter if it's an over or under prediction, adds to the total score. Nothing gets canceled out anymore.
So, this gives us our complete process for getting one single number. Step 1, for every single data point, calculate its error. Step 2, square every single one of those errors. Step 3, add all those squared errors up. We call that the sum of squared errors, or SSE. And finally, step 4, just take the average of all of them. That gives us one single, really powerful number, the mean squared error, or MSE. This tells us, on average, just how wrong our line is.
Now this is where it starts to get really cool. We can take that one number, the MSE, and we can think of it as an altitude. See, every single possible line that we could draw has its own unique MSE value. And if you imagine all of those possibilities at once, you get this vast three-dimensional landscape. And our job is to find the lowest point.
Oh, and just a quick heads up on the terminology here. As you dive deeper into machine learning, you're going to see a bunch of different names for the same things. That individual error, sometimes it's called a loss. And our main score, the MSE, that's very often called the cost function because it's a measure of how costly the model's mistakes are. It's all the same idea, just different names.
Hey, remember how we squared all the errors? Well, that one little mathematical decision has this huge, wonderful consequence for the shape of our landscape. Just like the equation y equals x squared gives you that classic U-shape, or a parabola, our cost function also takes on this predictable, perfect, bowl-like shape. And that simple shape is absolutely crucial for what comes next.
So, to put it a little more formally, we call our cost function J. And its value, the total error, depends entirely on the two things that define our line. Its intercept, which we'll call beta 0, and its slope, beta 1. All this means is, if you change the slope or the intercept of your line, you move to a new spot in the landscape, and you get a different total error. So look at what we've done. We have completely transformed our abstract goal, find the line with the minimum error, into a really simple, tangible, visual one. Now we're just trying to find the absolute bottom of this cost function valley. The coordinates of that lowest point? Well, that's going to give us the perfect slope and intercept for our best fit line. Okay, so we have our valley. But how does a machine actually find that lowest point? I mean, it doesn't have eyes. It can't just look. It can't just guess randomly forever. Instead, it uses an incredibly powerful tool to basically feel its way to the bottom. And that tool is calculus. And the key insight here is something that's actually super intuitive. Just imagine you're standing at the very bottom of a real bowl. If you look in any direction, what do you see? The ground is perfectly flat. There is zero slope. And this simple physical reality has a perfect mathematical equivalent. And this is where these two ideas just click together. In the physical world, slope is just about steepness, right? Zero slope means flat. Well, in the world of math, the tool we use to calculate the slope of an equation at any specific point is called differentiation. So, finding where the slope is zero is the exact same thing as finding where the derivative of the equation equals zero. This gives the machine a crystal clear three-step recipe. First, it takes the equation for our cost function value and it differentiates it. That gives it a new equation for the slope at any point. Second, it takes that slope equation and sets it equal to zero. And third, it just solves for the intercept and slope that make it true. The answer gives it the exact coordinates of that perfectly flat spot at the bottom of the valley.
So this entire process, this whole elegant system that we've been building up to this entire time, well, it has a name. And now we're ready to put it all together. There's just one final little detail. Our valley is really a 3D bowl, right? Because there are two things we can change, the intercept and the slope. To find the true absolute bottom, we need to find the one spot where the ground is flat in both of those directions at the same time. The math tool for this is called partial differentiation, which sounds fancy, but the idea is simple. Just check the slope for each of our parameters one at a time independently.
And that's it. This entire technique is called ordinary least squares, or OLS. And now that name should make perfect sense. It's the method of finding the best line by minimizing the sum of the squared errors, that's the least squares part, and it does it using calculus to find the exact point where the cost function's slope is zero.
But why does this matter so much? I mean, we went through a lot of steps there just to draw one simple line. Well, it's because this underlying concept, this idea of a cost function and finding the minimum, it's one of the most fundamental ideas in all of artificial intelligence.
So let's zoom out and look at the big picture. What do we really learn? We learn that we can define the best possible model by first creating a cost function that measures all of its mistakes. We learn that this function creates a conceptual landscape. And the entire goal of what we call machine learning, in this whole context, is really just the search for the lowest point in that landscape. And calculus is the powerful tool that lets the machine navigate its way to the bottom.
And this leaves us with a really fascinating thought to end on. We just navigated a nice, simple, predictable valley to find the best possible line. But what happens when the models get way more complex? What if the landscapes look like for models that recognize images, or translate languages, or even compose music? And how in the world do machines learn to navigate those infinitely more complex, rugged, and mysterious terrains?